presentation number 2, and I would like to introduce Ms. Ch3 who is a scientist and researcher and who works for the Thai Meteorological Department, focusing on tsunami modeling and verification. And her presentation today is the verification and modeling of tsunami arrival time and wave height along Thailand's Andaman Sea coast.
Okay, good afternoon, everyone. I'm Ch3 Promsuk from Earthquake Observation Division, Thai Meteorological Department. So today I will present on our study on the verification and modeling of the tsunami arrival time and wave height along Thailand's Andaman Sea coast using an enhanced toast. So let me start with a brief introduction. Thailand is not generally considered a tsunami-prone country, but earthquakes do occur, mostly in the northern part of the country, as shown in the map on the left, like the green dot represents the earthquake that occur. So, however, the seismic that capable of generating tsunami still exist and can affect Thailand coastline, which is the Sumatra-Andaman subduction zone. So this is a major source of tsunami risk to Thailand Andaman Sea coast. So in the past, the megahertz earthquake used to be occur and generate the tsunami. We know it is a 2004 Indian Ocean tsunami and have caused severe impact for people who live along the Thailand coastline. After this event, my organization got funding to establish the National Seismic Network to operate the real-time earthquake monitoring. And using the SeisComp with the TOS module inside, the TOS using for tsunami simulation. So the parameter in the TOS, the default one, are designed for the large scale or the global scale and may not capture the detail of Thailand coastline. So we set out the following objectives. The first one, to investigate the tsunami arrival time and wave height along Thailand Andaman Sea coast. Second, to enhance the bathymetric resolution from the 3.7 kilometers to 0.46 kilometers using GEPCO data. Third, to refine the impact area to subdistrict level. Four, to validate the simulation results with the target observation. And the last one, we would like to provide our tsunami information to another organization to let them warning people or support the evacuation planning. Let's see our study area. So, as I mentioned before, we focus only the Sumatra-Andaman subduction zone and Thailand coastline. You can see from the map that the yellow zone represents the subdistrict that we focus on. This is the impacted area for us. So all of the sub-districts that we focus are totaling 97 sub-districts that we digitize in the QGIS software. And for the tsunami scenario, we generate 4 epicenters. One of them corresponds to the magnitude 9.1, 2004 Indian Ocean tsunami, and we use the result from that to validate with the real target data. The remaining are the simulated event that we try to generate it for support evacuation planning. For the tools and method, as we use the SeisComp as a commercial version, they provide the tools inside. We stand for the tsunami observation and simulation terminal. It will generate a rupture area based on the Well and Copper-Smith equation, and it will calculate the arrival time and wave height using the model called easy wave. The easy wave introduced by the Kovalik and Whitmore and use the 4 parameters from the Okada. And it will generate the epicenter and then it calculates the arrival time of the tsunami and wave height for us. So the way we do it, we digitize the new forecast zone and forecast point by QGIS. We put it in the software. We put the new grid for us that we download from the GEPCO. And after that, we run the tsunami propagation simulation, and we compare the result with the target data. The picture in the up represents the shapefile data that we proceed in the QGIS, and the below it one show the simulation running in the software. Okay, the results are displayed within the RTSP format, Regional Tsunami Service Provider. Actually, the various output you can set it, but after we discussed with our team, we decided to provide 2 times, T1 and T3. T1 represents the time of accident of the detection threshold, which is set at 50 centimeters, while the T3 represents the time of maximum positive amplitude or the height wave arrival. The picture on the right shows you that the tsunami information that we will provide to public They show the T1, T3 wave height and the location the tsunami will arrive. This is an example of the result that we will provide, the tsunami arrival time map, wave height map, and the tsunami information. So let's see the result from the first epicenter that we used to validate with the real target data. This is the epicenter is the same at magnitude 9.1 earthquake that occurred in 2004. A comparison is made by comparing with the result from the research by the Supasi et al. 2010. In that paper, they provide two target stations that have two times, the first arrival and maximum wave arrival, in the two stations called Kuraburi Station at the Phang Nga province and Tapao Noi Station at the Phuket province. From the table, you will see that we will show the first arrival time and the highest wave arrival time. The record one shows the real time from the target station, and the model one represents the time of the model from the old bathymetry and the improved bathymetry. And asterisk represents the data based on improved bathymetry. And the gray zone represents the difference between the model and the record. So for the first arrival time, show no significance between the default bathymetry and the improved bathymetry, just about 30-minute differences, while high wave arrival shows significant. If you see between the record one and the model, the old one, they have 2 hours and a half difference, while when we upgrade the bathymetry already, it's closer. From the Kuraburi station, it comes 9 minutes earlier, and for the Tapao Noi station, it comes 28 minutes later. So it can prove that if we try to improve the bathymetry, our model is more accurate than the default one. For the earliest arrival from all of the epicenter that we generate, it shows the same result that Lam Kan Sub-District, Thai Mueang District, Phang Nga Province is the first location that the tsunami will arrive within 1 hour. For the maximum wave height, show that they show various locations that tsunami will arrive. But if you try to look at the first epicenter, that the same location with the 2004 Indian Ocean tsunami, the maximum wave height reaching about 10 meters. Try to compare with the real data from the Ch3 et al. 2006. They went to the field and they record that at that time tsunami reaching up at Thai Mueang, Thung, Got Pha Thong, Phang Nga province about 19.6 meters, while other area was less than 10. So for the wave height, it's our challenge in our future study. We'll try to make it more accurate. But now our team say that it's enough for the early warning stage. So it can use to warning people if the earthquake that can generate tsunami occur. It leads to the conclusion. We modify the TOS model. This is a module in the SITECOM, and we improve the new bathymetry resolution, digitize the new forecast zone and forecast point into sub-district level rather than use the old one that is larger, and we try to compare with real target observation data. So the arrival time of the first wave shows no significance, while the maximum wave height closer to the record data. Among the other simulated epicenter, show the same result that Lam Kan Sub-District was the first location that tsunami will arrive. Let me admit that I'm not have the basic of the hydroacoustic, but I try to validate the data with the IMS data. So although we validate our validation model based on use the local target, but the tsunami sequence also aligned with IMS data. As the paper of the Tolstoy Bonensto 2006, they said that T-wave will arrive at the Diego Garcia South in 32 minutes. So after that, they will reach at the Thailand coastline. So this our challenge. It leads us to our future plan that we will try to integrate the multiple bathymetry dataset for the higher resolution. Because we cannot compare the time directly with hydroacoustic data because of our bathymetry is not cover that area of that station. So maybe in the future, if I can try to expand our grid, we can compare it directly. For the second future plan is refine the forecast zone from the sub-district level into village level for the precise impact prediction. Third, to enhance validation with the additional observation data. And the last one, because now we use the default model called Easy Wave. Maybe in the future, we will try to develop our own model or maybe TMD model in the future, make it more suitable for Thailand coastline. So I think that's all for my presentation today. Thank you very much.
Thank you very much, Ms. Chutimon. Let me just ask the floor for questions. Catherine.
So I have a question. Actually, I have two if there's time. My first one is, you mentioned fault parameters of the earthquake. Did you use the same set of fault parameters for the original 2004 earthquake and then the 3 simulations?
Actually, we try both. We use the default parameter from the Well-Coppersmith equation, and we try to put the fault parameter from the USGS. Like the first arrival, the arrival time show no significant, both of the simulation result, but for the wave height have significant.
And the simulations all use the same set of fault parameters as
Yes,
well? Oh, okay, thank you.
Any other questions?
Yeah. What do you need to change? What do you think is the most important change that needs to be done on EasyWave to adapt to, as you said, the Thailand coast in your case?
Mm-hmm. In my opinion, I think if we can develop our own model, it's more suited for my country rather than use the EasyWave. Do I answer the question?
Yeah. I was just wondering because I don't know what it comes with the default EasyWave model compared to what you would like to use.
Yeah, because EasyWave is set for the global scale. If we can make it more detailed with my country, is better.
Okay, thank you.
Thank you for your question. Any other question? I have one question, very simple one. Thank you. You demonstrated the enhancement of bathymetry has a big impact going through, I think, just over 3 kilometers to less than half a kilometer. How much further do you think is possible to take that resolution?
You mean in the future?
Yes.
Of course, high resolution require more computation runtime. If we can, in my opinion, we try to make like high resolution near the coastal line, and if we're far away, I will try to reduce the resolution to make it like, less time for running. If it can reduce to like 0.2 kilometers, or maybe it's gonna be work. Just only my opinion.
Thank you. Have you got any more questions for Chutimon? If not, let's give it a round of applause. Thank you very much. Thank you.